Hi everybody, thank you so much for coming. So we'll continue. So today we'll teach math. It's a math class. And we'll see how is it useful next class, right? So, you know, whenever you talk about network security, the first thing you have to talk about always is primes, right? Primes. Okay, so what's a prime? It's a number, a digit that is divided by itself. It's divisible, let's say divisible by itself. And 1, right? So, is 0 prime?
No.
No. Is 1 a prime?
Yes.
No. Because it divides by itself, but not by one. By it's not considered. All right. It's not considered. How about 2?
Yes.
Yes. Okay. 3. Yes, and so on and so forth. 10. Oh, yes. 10. No. Okay. So we work with the primes a lot. We work with the prime a lot. So usually when the numbers could be positive integers, so number 1 is exactly 1 divisor. Primes, they have exactly 2 divisors, and composite we have more than 2 divisors, right? All right. So the other let's talk about CoPrimes. Okay, CoPrimes. So, what is a CoPrime? Okay, CoPrime. Okay, what are CoPrimes? All right. So two positive integers a and b are relatively primes or co-primes. That's the other word is relatively primes. Okay, they are relatively primes if we have a and b. For example, they are relatively primes when you know the greater common divisor for a and b is 1. The greater common divisor for both are 1. Alright. So for prime numbers, how many, if you have a group of primes, so this for example z, okay, b, right? A group of a prime, okay, how many elements first we could have in here? How many elements? 1, 2p minus 1, right? Right? If you have z, for example, 5, right? So you'd have, what are the set will have 0, 1, 2, 3, 4, right? Right? Only because it's a prime, right? So when how many co-primes we have here in a group of primes? All of them are co-primes. So Z5 has 5 elements in here, and all of them co-primes, right? So if we have a group like this, Zn, okay, how many co-primes we have?
-1.
We don't know because we are not sure if this is a prime, right? Right? So if it's 5, we know. If it's 3, we know. If it's 8, we don't know, right? Because it's not a prime. All right. So that's what is a co-prime, right? All right. So the question is, all right. So primes start from 2, 3, 5, 7. You know. The question: is it in infinity, goes to infinity, or there is a number called the most large or the largest prime?
Infinity.
It's infinity. Okay, it goes, of course it's not infinity, but the numbers, there's a huge number of primes. Alright, so when we work with security, what we look for? Prime numbers, because of their characteristics, right? What is the major problem? Finding them. Okay, so if I give you, for example, of course, when you do encryption and security, you're not going to use like a key like 7, right? We're gonna use like a key like this: 7, 9, 8, 3, 1, 4, 3, 1, 2, 5, 6, 7, 8, 9, 1, 0, 1, 10, okay, and you kind of look like maybe like the end 9, 8, 7. Okay? How can you know if this is a prime or not a prime? Okay, so many of the algorithms you have to have a prime, right? Okay, so how can you determine a number is a prime or not a prime? Alright? So that's the first thing, that's the challenge, that's the major challenge that you have to tackle. Alright? As a trivial example, assume that, okay, whatever. Alright. So let's talk about the number of primes. Okay. All right. All right. So if you have a number n, all right, and if I need to know the number of primes less than n, so for example, if n equals 10, for example, phi of 10 is the number of digits, okay, that less than 10 but they are primes, right? So that's what's phi n, okay? So what are they? 2, 3, 5, 7. How many? 4, right? If it's like if it's in like a huge, large, okay, how can I know it? All right. So for example, also, okay, phi of 100. Okay. Of course, this is wrong. This is 4. It give you a number. Okay. Phi of 100, how much? 25. So there's 25 primes, okay, less than 100, okay? There is 25. So the question is, if I need to know how many primes less than a number, how can I know that? How can I know that? All right, so there is, there is a few rules that could tell you that, okay? Okay, so one of them is Gauss discovered the upper limit, Gauss. So the rules usually here we're working with deterministic approaches, okay, and probabilistic approaches, right? So which one you think is much more efficient? Probabilistic, right? But the problem, they don't give you 100% assurance the answer is good, right? So that's usually what we gonna deal with. Okay, the question is, so how can we know, or what is the maximum number if I have 100, for example? Okay, 100 is then easy, but what if I have a number like this? And I need to calculate the pi for it. So, a scholar called Gauss discovered the upper limit. Okay, Gauss. give you the upper limit. And another one, Lagrange, give you the lower limit. And the upper limit is, or basically the upper limit and lower limit, so by n, it should be greater than, okay, n divided by len of n. And the upper limit is n divided by len n minus 1 minus 1 0 8 3 6 6. I'm not sure if you can read my right. So that's the lower limit and that's the upper limit. So this is like you know the range of number of primes in that number. Is it still useful? Is it useful? Maybe. If you think it's useful, then it's useful. If you think it's not useful, keep your opinion for yourself. I'm not telling you. All right. So we'll see. So for example, find the number of primes less than 1 million. So if you have 1 million, what are the number of primes? If you apply this rule, you'll find the range will be 72, 83, 383, okay, to 78, 543. That's the range, right? And the actual number is 78, 498. That's the actual numbers. So there is close to 80,000 numbers, primes, less than a million. Okay, less than a million, right? I'm sure you know what is the first prime, right? You know? 2. All right. All right. So checking for primeness. Okay, so that's how to find. In the first section today, we're gonna work a little bit with the primes, right? Because that's the trick. When we go to the next section, or not section, next chapter, all right? RSA, for example, the whole thing the whole algorithm starts by finding 2 primes. All right? The examples we give in the book on anywhere to study small primes, just to make you comprehend what's going on, right? But in the real life, the primes are huge. So you have to check if this is a prime number or not a prime number. Okay, you should be able to check if it's a prime. So there is, many ways or many algorithms try to check if you are given like a prime, right? Can check if it's a prime or not a prime. Okay. So definitely, what is the first way to check if the number is a prime or not a prime? Divisibility, right? So if you try to check, right? You try, for example, is 10 a prime or not a prime, right? So it has to be divisible by itself or 1. So you try with 2. It's not prime right away. How about 11? You start with 2, no. 3, no. 4, no. 5, no. 6, no. 7, no. 8, no. 9, no. 10, no. 11, yes. Then it's what? Prime. All right. But if you have a huge number, you'd like to check it's prime or not prime. Okay. It takes you forever to check if it's a prime or not prime. So that's not the way to do it, right? Okay. So one way is divisibility prime. Okay. So you check for the root of n. The root. So given a number n, how can we determine if n is a prime? The answer is that we need to see if the number is divisible by all primes less than the root. Okay. So for example, if I need to see if 100 is a prime, right? So what's the root of 100? Equals 10, right? So I need to look at the primes less than 10. What are the primes less than 10? 2, 3, 5, 7. Alright. Is 100 divisible by any of these?
Yes.
Yes. Then it's not a prime. So I don't have to check all the numbers from 1 to 99 to check it. Okay, just I get the root and see the primes less than that root, I'll try it out. Okay, so so for example, another example in here says like it's 97, for example, 97. So what is the first thing you have to do? Check the root. What's the root? Okay, 9. All right. So what are the primes less than 9? 2, 3, 5, and 7. All right. So is 9 divisible by any of these? 3, right? Then it's not a prime. It's not a prime. Right? Another example. Okay, 301. So 301. What's the first thing you have to do? The root. It'll give me 17, right? So what are the primes less than 17? Okay, 2, 3, 5, 7, 11, 13, 17. So, is there any of these could divide any of these? Okay, could divide the 97? I'm sure divide the 301. I mean, sorry, here the 301. And if this could divide the 301. Does 2 divide the 301? No. 3? No. 5? No. How about 7?
Yes.
Yes. So 7 divides it, then it's what? Not a prime, and so on and so forth. Okay? Good so far? Makes sense? Alright. Then another guy called Steve. Elitosny, I think, in the name and all of that. So basically, you create a table. Everybody has a book with him? No? Why not? Okay. All right. So I could go to the PowerPoint, but I like to write more. When it's math, it's better to write. Okay. So Sif of Eratosni, I think I forgot to check how they said that. So you could create a table. Write down all the numbers between 2 and 100. Okay, and you could cross it like. Let's go to the PowerPoint. Alright, so Sith and Eratosny, I think, alright, So you arrange, you arrange all the numbers. You arrange all the numbers in a table, okay? And anything is divisible by the numbers. So I mean, what are the? This is for 100, right? From 1 to 100. Of course, you don't include 1 because it's not a prime. 100. And the point in here, you need to find, for example, the prime less than 100. So put them in a table, all right? And for the root of 100 is 10. What are the primes less than 10? 2, 3, 4, 5, right? The primes less than 10, it's like 2, 3, 4, sorry, 5, and 7. Okay, 4. And any number in here is divisible by these, just cross them out. The remaining will be what? Prime numbers. So 3, okay, it's a prime number. 5 is a prime number. 7 is a prime number, and so on and so forth. Right? The problem is this is for 100. It took you this effort, right? Can you imagine that you have, like, if I need to know the primes less than 1,000 or less than 1,000,000, maybe it's not useful to use this way, right? So let's go to Euler phi function. Euler phi function. All right. So we can combine the above 4 rules to find the value of phi n. Let's go here. Okay, Euler phi function, phi n, which is sometimes called the Euler's twotent function, plays a very important role in cryptography, and this is something you have to master. So phi of 1 is 0. Okay, phi of p, what's p? Is a prime. So it will be, okay, p minus 1 if p is a prime. Alright? If it's not a prime, we have to find multiples for it, and they are primes. Alright? We'll see example. So if the number is not prime, okay, I have to find 2 multiplications that they are prime. They are prime, and then in that case I'll find the phi for the m and the phi of m, multiply them together. If it's a prime to a power, then the phi will be power of e minus the power of e minus 1. Visiting example. Visiting example. So in here also, if you can have n to be factored to multiple primes to certain power, so the same thing, you gotta take the first one and the power minus the p minus the power minus 1, and so on and so forth. So the best thing example, let's take examples, alright? So phi of 13, okay, what is the first thing you have to check? Is 13 is 13 is it a prime? Phi of 13. So is 13 a prime?
Yes.
Okay, so what's the rule says? P minus 1, right? Which is 13 minus 1 equals 12. Okay? So the phi for the 13 is 12. About 10. Is 10 a prime? No. Can I make it like a divided in 2 numbers that they are primes? Okay, which is 2 and 5, right? So phi of 10 equals phi of 5 multiplied by phi of 2. So phi of 5 is equals to what? 4 times 1 equals 4. Alright? Alright. So now the value of phi 240. Is 240 a prime? No, right? It's okay. So how about if I 240, if I make it like 240 for example, phi of 240 equals to what? Equals to power what? Can't see 4. Okay. Times 3 to power 1 plus 5 to power 1. So I was able to factor it to 3 primes, right? 3 primes. So which rule I have to use? The third rule, right? The third rule. What does the third rule says? 2 to the power 4 minus 2 to the power 3 multiply 3 to 3, 3 to the power 1 minus 3 to the power 0, and then 5 to the power 1 minus 5 to the power 0, right? Okay, so 2 to the power 4 how much? 16 minus 8, which is 8 times 3 times 5. How much? 60. What? It becomes like 64, right? Alright. So let's take another example. We can say that, okay, 49, okay. So 41 equals to what? 7 times 7, right? So a prime times prime, right? So what is the 576? What is the 576? 36. Is that correct or wrong? Wrong. It has to be 2 different primes. So what we should use, the other technique, which is 7 squared. 7 squared prime to the power. So what we do, yeah. So it will be it will be 7 to the power 2 minus 7 to the power 1 becomes 42. So remember that in many algorithms in the future, you're gonna need to calculate what? The phi. Okay, so few rules that you have to note down. Alright. What is the number of elements of Z14? So is 14 a prime? No. Right? So what? So you have to calculate the phi for it. So what's the phi? The phi of 14 equals, the 14 equals 7 times 2. 7 is a prime, 2 is a prime. So phi of 7 is 6. Phi of 2 is 1. Then equals 6. So the numbers are 1, 2, 3, 5, 9, 11, 13. So these are the so what phi does? It calculates the number of coprimes in the group. The number of coprimes. The number of coprimes, right? So what does it mean coprime again?
Greater common denominator is 1.
Is 1. Okay, is 1. So interesting point that if n greater than 2, the value of phi n is always even. Okay, so if it's n, so n for example in here is 14, is it even? Is it greater than 2? Yes. So the number of elements that they are coprimes are even. All right. So what we learned so far. All right. So we learned what is a prime. We learned a few techniques how to find how many primes less than that number, and we try to also to find a way to find primes less that number. So how many, which is by of that number, and what are the primes. All right. Then we need to know for a group, we need to know how many relative or coprimes it has. How we do that? By calculating the phi. Calculating the phi. All right. What is phi? Okay. What is phi?
Coprimes?
The Euler function. It's the Euler function. Okay. Simple. Moving forward. All right. So now we move from Euler to Fermat's little theorem. Fermat's little theorem. Okay. So there's 2 versions, version 1 and version 2. Version 1 says Okay. So, and here the modulus is, we're talking about modulus which is a prime. Okay, it has to be prime. So it says that, okay, a to the power, a to the power modulus minus 1. So the modulus in here is repeated in here. Then the result will be 1. Will be 1. The second theorem, it says that a to the power p, okay, equals the a modulus p. Modulus p. Alright. So let's take examples. So find the result of 6. So for example, in here, alright, 6 to the power 10 mod 11. Alright. So the simplest way to do it for yourself is to have a calculator. Okay, 6 to the power 10 mod 10, right? But we need to use Fermat's. So what is the prime here? What is the modulus? I'm sorry. 11, right?
Mm-hmm.
Right? Is it a prime? Is it a prime? It's a prime. So what the first rule says, that modulus prime, if the integer is raised to the prime minus 1. So in our case it was 11, this has to be 10, right? Has to be 10. So that's exactly what has happened, all right? So 6 to the power 10, 10 is a prime minus 1, the prime or the modulus is 11, then what should be the result? Without even doing any calculator.
1.
It's 1, right? So what does it say? Okay, the rule says, okay, so mod p, anything raised to p minus 1, okay, then the result is what? 1. Our example, mod 11, and we have 6 to the power 10. This is 11, okay, which is p, and 10 is p minus 1. So what should be the result? 1. Okay, have 20 to power 10 modulus mod 11. What will be the output in here? 1. Okay, have a number like this. So, okay, what will be the output? 1. Doesn't make difference. So you don't have to get tired to calculate the modulus, right? So okay, clear? Let's take out the other example, the next example. 3 to power 12, okay, mod 11. Okay, so what we do with this? We have to factorize it a little bit, alright? So we say the 3 to power 12 could be 3 to power 11 multiplied by 3, mod 11. Then you have mod 11 to the mod 11 multiplied by 3 mod 11. So the 3 to power 11 mod 11, which rule? Is the second rule, okay, which is in here. That means if it's a to the power p, then the result equals a if the modulo is b, right? So the 3 here, the 3 11 mod 11 will be 3, and the 3 mod 11 will be 3. So 3 times 3 will be 9. Will be 9. Clear? I mean, you could stop me anytime. I'm gonna keep flying. If you don't stop me, I will understand that you are okay with it. Okay? All right. So now, one of the techniques that we need to learn how to use, multiplicative inverses, right? So we know how to do it with Euclidean, right? The Euclidean algorithm we used before, right? All right. But it's a very complex Euclidean, right? So maybe we could use it with the Fermat theorem and all of that. Okay. So the multiplicative inverse says that to calculate, so a to the power minus 1, that means it's multiplicative inverse. It will equal to the p minus 2, okay, mod p. Let's take examples. Alright. So I would like to calculate the multiplicative inverse for 8 mod 17. So what does it equal to? From the rule, take a rule in here, right? It will equal to the p minus 2. What's the p? 17. So we put 8 to the power 17 minus 2, which equals to 8. 17 minus 2 will be 15. So 8 to the power 15 mod 17, that will give you 15. So what is the multiplicative inverse of 8?
15.
15. Okay, it's 15. What's the multiplicative inverse of 15?
So
Mod 17.
how do we get from 8 to 15, mod 17 to 15, mod 17?
So when you do the 8 to the power 15 mod 17, it will give you 15.
Why?
Use your calculator. Give you 15. Alright?
Okay.
Yeah, that's what it is. Alright? Let's take a look at the second example. Okay? What is the multiplicative and multiplicative? I mean, we have to ask the question the right way. Alright? Sometimes myself, I'm giving answer mixed with the question, so everything becomes wrong. Okay? Because I'm thinking one way, but I'm asking two. Alright. So, what is the multiplicative inverse of 5 modulo 23? That's a good question. So always you have to mention the modulo, right? So the same thing. So 23, is it a prime? The modulo is a prime, right? It's a prime. So it will equal to 5 to the power 23, the prime minus 2. That will equal 23 minus 2 will be how much? 21. So 5 to the power 21 mod 23, which is 14. That means the multiplicative inverse of 5 modulo 23, it will be 14. And there is other example we could follow. So what did we use? We use a simple algorithm in here, simple thing that we have to remember. In many algorithms that we're gonna use, we're gonna need to calculate the multiplicative inverse. Alright? So this multiplicative inverse, you could calculate it with this formula under a few conditions. What are the conditions? That the modulo is
Prime.
prime. It has to be prime. If it's not a prime, you cannot do it, okay? Alright? That's it. That's the only condition. It has to be a prime. Alright? So it's a great gift for you. If the modulo is a prime, you could easily calculate this. Alright. Alright. So and here we come to Euler's theorem. We're moving to theorems. Euler's theorem. Okay, what Euler's theorem say? It says that. Okay. And Euler's theorem, it does not talk about prime. It talk about an integer, n. Okay, integer, n. It's just like a generalization for the previous one. So, if you have integer power 2, phi of the n. How we calculate the phi of n? What is phi of n?
The formula we saw.
The formula we calculated before,
Phi.
right? In here, the phi of n. Okay, what does mean? What does phi? I'm asking just. I want to make sure that you're. I'm not testing you, but I want to make sure you are awake. If not awake, just make you run. All right. So phi of a number. What's a phi of number? Number what?
Number of primes before that.
No, number of coprimes. Number of coprimes, right? So any number, if I need to know the number of coprimes in that set, okay? Okay. So the rule says in here, okay? So if I need to know the modulo n, okay, of any number raised to the phi of that number, to the phi of that number, it will equal 1. It will equal 1. You could take the proof in the book. Enjoy. Alright? The other one, the bigger one, so in here, if you have the modulo n, then any number, any digit, to the power of k, which is any integer, 5n, n is a modulo plus 1, it will give you a. So the second version of Euler's theorem is used in the RSA cryptography, which we're gonna use next week. Which we're gonna teach you next week. Alright? Let's take examples for that. So find the results of 6 to the power 24 mod 35. Which rule we have to apply here? So if I calculate the phi of if I calculate the phi of 36, how do I calculate phi of 36?
36 or 35?
Is it 35? I'm sorry. Is 35 a prime?
No.
No.
7 times 5?
5 times?
7.
7, right? So it will equal to 4 times 6, which is 24, right? 24. And what I'm trying to calculate in here?
CoPrimes.
Okay. 6 to the power the phi of the 35. So the 24 is what? The phi of the 35. So what is the result? Without doing any math?
Not
1.
1.
Alright? It just has happened. We have a modulo 35. Its 5 is 24. Any number to power to phi of that number, that modulo, it will be 1. You don't have to work hard for that, okay? So that's what we did. Let's take a look at this example. Alright. So 20 to the power 62 mod 77. Alright? So what we do in here, if we let k equals 1, on the second version we have 20 to the power 62 mod 77. So you have a 20 mod 77, so we need to divide this little bit, right? Okay? Alright. So first of all, what is the phi of 77?
60.
60, right? So 60, okay, so I took this separate in here, and this is 60 plus 1, right? 60 plus 60 plus 1, right? Mod 77. So I calculate 20 mod 77, how much? 20. This is applied from the second rule. If you have a integer raised to k, which is 1, it happens 1 in here, times the phi plus 1, it will equal to what? To the integer itself. So 20 times 20, 177, okay? And then 40, 170. How 15? Should be 40, right? 20 times 177 should be, oh, 400, so it will be 15. 400 modulo 77, it will be 15. So let me go back to the previous, which one we have used? We have used this one. So a to the power k. What was our k? 1. Phi n, how much phi n? 60 twice. Plus 1. So what we did in here, okay, 1 times 60 plus 1 plus 1 times 60 plus 1, 61. However, how much I have? 62. So I put the 1 alone. I did it alone. Alright? Right? And we did the rest. Okay. So again, how can I calculate the multiplicative inverse? Same thing here. Okay. So a multiplicative inverse modulo n. The previous one it was specialized is modulo p prime. Here n, any number, it equals to what? To the a power phi n minus 1 modulo n. Okay, modulo n. So it's a very easy to calculate. Take example in here. So multiplicative inversion modulo a comprise can be composite can be found without using the extended Euclidean algorithm if we know the factorization of that composite. Alright, so you have to. So for example, the first example, I need to know the multiplicative inverse of 8 modulo 77. So I have to arrange it a little bit. So it will equal 8, okay, to the power 77 minus 1. Okay, 577 minus 1. We calculate the 577 minus 1, it will give me 59. Modulo 77, that will be 29. So from here I know that multiplicative inverse of 8 modulo 77 will be 29. Same applies for the rest. Right? And by the way, I mean, if you think that is a tough math, I mean, that's the easiest math you could have when you come to cybersecurity and algorithms and cryptographics, alright? So I'm sure that when you go through the book with the examples and you do the homework, you'll enjoy it, and it will be fun. Alright. So far, just to refresh your memory one more. So we started with Euler phi function, how we calculate the phi function, and then after that we spoke about Fermat's little theorem, and we moved on to Euler's theorem, okay, and we took a few examples, right? And now we come to the point generating primes. We need to generate a prime. So when you're creating public, two keys, let me give you the idea why we are doing that. So in the previous lecture, or lectures, we were talking about public cryptography, right? Actually private cryptography. That you have one key shared, alright? Could be anything, as long as it's like 64-bit key or 256, depends on the protocol you are using, right? Now we are talking about private cryptography. Private cryptography, how many keys you gonna have? 2. One of them is public and one is private. Alright? And you could lock with any of them, but if you lock with one of them, you have to unlock with the other one. Alright? So the whole talent in picking what? 2 related keys. And these 2 related keys usually has something to do with the primes. So if you have part of the key, the other destination will be able to calculate the key. So 2 keys, one can lock, one can open. We are proceeding or progressing toward this knowledge. Alright, we have to understand all of these theorems, how it works, you know. So usually when you start about RSA, it starts with 2 primes. Pick 2 primes. And then there's multiple steps. Alright, we create that, right? So it's a very important to understand this kind of math, to understand the following algorithms we're gonna cover. Alright, so from what I said, that we have to generate primes. Okay, generate primes. If I tell you, let's create public key, private key, let's generate 2 primary keys, you tell me 3 is 7, that's good. But nothing will be secured. This is too small, right? You're talking about keys which we are 500 digits each. Okay, all right. So how to generate the primes? There is different rules to generating primes. The first one is, for example, okay, in here, Mersenne primes. I mean, this it says in here that a prime number it equals 2 to the. So if you have, for example, n2, so any number 2 to the power of that prime will give you another prime. So for example, is 2 a prime? Yes. 2 to 2 minus 1, 3. Is 3 a prime? Yes. How about 3? Is it a prime? Yes. 2 to the power 3 minus 1, 7. Is 7 a prime? So we're trying to generate more primes. So do you think this algorithm will go too far? Unfortunately, no. So if you try it here, it fails in here. Okay. So 2 to the power 11. Is 11 a prime? Yes. It generated 2047. And 2047 is not a prime because you could factorize it to 23 times 89. Okay. So a number of in the form np to the power a minus 1 is called Mersenne number, or may not be a prime. May or may not be a prime. Alright? By the way, you know what is why we have to have like a large prime number in our algorithms? Because if the cryptanalyst is able to factor it, you're done. So it has to be so large that cryptanalyst cannot factor to two numbers, like in here. So if using, for example, I move the slide, the number before we're able to factor to two numbers, that's a problem. All right? 2 primes, okay, what's a problem? All right. All right. So in here, all right. So then after that, there's something called Fermat primes. Fermat primes. So Fermat tried to find a formula to generate primes. The following is the formula for a Fermat number. So what Fermat says, look at the board there. If n, if you have a number, so n to the power n to the n plus 1 is what? Is a prime. Alright? I mean, we wish we have rule, concrete rule. There is none, by the way. It's all, it could give you a number, but it's not 100% will be a prime. It's not 100%. So for example, if 0 will give you 3. Why? Because 2 to the power 2 to the power 0, it will give you 2 plus 1, 3. Alright? When you go, for example, to F5 in here is not a prime, it's failed. Alright? So if you use the Fermat primes, yes, it will give you a lot of primes, but there's no guarantee that all of them are primes. Alright. So now we move to primality testing. So when we need to have a number, we need to test if it's a prime, right? So as we said, there is deterministic algorithms and there is probabilistic algorithms. Okay, well, we will cover a few in here. Okay, so for the deterministic algorithm, what is the first one will be? Divisibility algorithm, right? Alright, so you try all the number, list that number. If it divides by other than itself on the one, then it's not a prime. This is not practical. It's not a practical, it's a complex. Complex. So this bit, the bit operation complexity of the divisibility test is exponential. So the larger the number, the more complex. All right. So definitely is not practical. All right. So let's take example in here. Assume n has 2 bits, right? What is the number of bit operations needed to run the divisibility test algorithm? So the bit operation complexity of this algorithm is 2 to the power n number of bits over 2. So you have 2 bits, 200 bits, that means the complexity is 2 to the power 100. 2 to the power 100. So that means if I have like a computer that could operate in 2 to the power 30 bit operations per second, how much time am I gonna need? 2 to the power 70 seconds just to finish that. That means it's gonna take years. Okay, it takes a lot of time. So it's not practical, all right? The other technique, which is deterministic, which is AKS algorithm, so it's not explained in this textbook, but they give you what what is the algorithm, how the complexity of the algorithm. And in here, I mean, what it's trying to tell you, I mean, you have to know the primes, different techniques to generate primes, the complexity of generating primes, right? Complexity of factorizing and all that, just to understand the things, okay? So the complexity in here is O log 2 NB to the power 12, all right? The previous one was how much? N over 2. E, it was exponential E to the power N over 2, right? It was E N over 2, right? To the power N of 2, right? So definitely this is like a log, so it will be faster, Let's take the same example. Assume N has 200 bits. What is the number of bit operations needed to run AKS? Assuming the same situation. So the algorithms need log 2 to the 100 to the power 12, that it will be that much bit operations. And the computer capable of running 1 billion bit operations per second, the algorithm needs only 40 seconds. We need 40 seconds. 40 seconds. Is it too much or too little? Huh? It's too much. Can you imagine that you need to encrypt like all your hard disk drive? So definitely in terms of encryption, it has to be much, it has to be in microseconds, just to get the prime. Remember, microseconds. So 40 seconds is a lot. It's impossible to do this way. Imagine that you need to encrypt something, decrypt something. You have to wait on the computer like 2 minutes until it's gone. It does not work like that, right? All right. So definitely we have to have better ways. Okay. All right. All right. So these are deterministic. They are not practical. They are sluggish, slow. So we have to use what? Probabilistic algorithms. You agree? All right. So what is the problem with the probabilistic algorithms? Okay. So if the problem with the so basically what we are trying to do in here, what is the goal? What's the input? A number. What's the output?
Prime.
Prime or composite. So the output is gonna tell us this number is a prime or a composite number. You agree? All right. So if the integer to be tested is actually a prime, the algorithm definitely returns a prime. However, if the integer to be tested is actually a composite, the return a composite with the probability 1 minus epsilon, okay? 1 minus epsilon will tell you it's a composite. So yeah, definitely will tell you something. But there is epsilon chance, will tell you epsilon chance. Epsilon means little probability. It will tell you this number is a prime, but it's not a prime. So if it's a prime, it will tell you it's a prime. But if it's a composite, 99.9% will tell you what? It's a composite. But there's still a little chance will tell you it's what? Prime. Okay? That's what we call it, probabilistic algorithms. Alright? So in this situation, you know what I'm talking about, right? So, one more time. So if the number n, okay, you test if it's a prime, so f prime, it will tell you 100% it's a prime. If n is a composite, so 1 minus epsilon, it will tell you it's a composite. And epsilon will tell you it's what? Prime. That's wrong, right? But it's a very low probability, right? How can I reduce the epsilon? By doing the test multiple times, right? So if I do the test multiple epsilon, if I do it twice, the probability will be epsilon squared. If I do it 3 times, 3. If I do it 4 times, 4, right? So if the chance that the epsilon is 0.1, if I do it twice, it will be, okay. If I do it again, okay, it will be what? Okay, the chance will be less. Okay, so by repeating the test with different parameters, I could reduce the epsilon. You agree? I feel like you guys love math. You don't like having it today. Alright. Anyways, so let's take a look at Fermat test. Fermat test, if n is a prime, then okay. So we already covered Fermat test. So what's Fermat test say? Take a look in here. If n is a prime, then a to the power n minus 1 modulo n will give you 1. So if n is a prime, a to the power n minus 1 is 1, 1. If n is a composite, it is still possible. It is still possible to give you the result as 1. So if it's a prime, 100% will give you what? 1. If it's not, if it's a composite, it could be 1, could be something else. But still there's a chance it will be 1. So take example here, does number 561 pass the Fermat test? So the number passes the Fermat test, but it is not a prime because 561 equals 33 times 17. It passes, all right? What does it passes? That means we did mod for what? 561, and in here whatever digit in here, okay, for 560. All right. So what was the result? 1, right? So what you would think that this is what? A prime, but it's not a prime.
So, you said if you do it again, you lower the probability.
Sure.
Are you going to get the same answer?
No. Change the A.
Oh, change the A.
Keep changing the A.
You changed it.
Yeah. Never try the same thing twice. All right. Does the number 561 pass the Fermat test? So in here, 2 to the power of 561 minus 1, 1, okay. So it will, okay, did not, we did that. All right. So, so the first one is Fermat. So now we are going through a series of techniques for what?
Testing prime?
For what?
Testing prime?
Finding out if it's a prime or not, testing the prime, right? And it's probabilistic, right? So the first one is Fermat test. The second one is square root test. Square root test is, in the square root test, in n is a prime, then the root of 1 mod n, it will give you plus minus 1. If n is composite, the root of 1 mod n plus minus 1, and possibly other values, So basically, so what you do, take a look at the example here. The only square roots are 1 and minus 1 we can see. So for example, this is modulo 7, all right, 7. So what are, okay, is 7 prime? So prime, what is in the set there? How many numbers in the set? 7, right? What are they? 0, 1, 2, 3, 4, 5, 6, right? All right. How many of them are coprimes?
6.
All of them. Right? All of them, why? Because it's a prime, right? Okay. 6 actually, you're right. 6. All of them except the first one. Okay, because how we calculate the coprimes? 5 of 7. What's the 5 of 7? 6, right? Okay, 6, right? Easy, I mean, we're just following step by step, right? So in here, what you do, so 1 to the power 2. So in here, if you remember, to the power means what? We repeat the operation twice. So 1 times 1, mod 1 will give you 1. 2 times 2 mod will give you 2 power 2 is 4, will give you 4, okay, 3, okay. Same thing in here, if you do it with the minus 1, it will give you, so basically, alright, so basically it's in here, okay, it will give you 1 and give you 1 in the minus 1. It's not repeated, so it's only in, it gave you a root of 1 mod n twice for the 1 and the minus 1. Then it's what? Upright. Then it's upright. If we have seen another 1 in here, or here, or here, then it's not upright. It's not upright. Maybe there's another example. Let's take a look at that example. What are the square roots of 1 mod n and n7 prime? And that's what we already saw. So note that we don't have to test 4, 5, 6 because, you know, 4 it's like minus a 3, right? Right? So minus a 3, if you convert it to positive, how you convert it?
That's it.
Add 7 to it, which is 4, right? And so on and so forth. Okay, what is the square roots of 1 mod n in 8? So in 8 now, there are 4, 8, you have to calculate the 5. So the 5 for 8 is how much? Is 8 is a prime? No, right? Okay, so anyways, so it's 1, 3, 5, and 7, and when you do the same thing, you see 1, you see 1 in here, but you see also 3 to the power 2 give you 1, and give you 1 in here, alright? So this is not upright, it's not upright. What are the square roots of 1 mod n if n is 17 and 17? Alright, so you do the same thing, the same process we did there, and you see 1 at 1, there's 1 value for 1 value for the minus 1, then it's 1. Another example. Okay. So this is the second one. The third technique, you would like to have a break? Break?
Sure.
Just have a break. About the probabilistic algorithms. We covered the Fermat test and we covered the square root test. And number 3 is Miller-Rabin test. Miller-Rabin test. Okay. So this is. So let me try to explain it, but you might need to go over the book because it's a little bit involved. So in the Miller-Rabin primality test, combines both of the previous methods, the Fermat and the square root. The Fermat and the square root test. So basically, what we're trying to do, we're trying to find. If we're trying to check on n, we need to find 2 digits, which is m and k, that n minus 1 equals m times 2 to the power k. Alright? So if you look, if you remember that the Fermat's method, what does it say? It says if we have mod n here, mod n and a, all right, to the power of n minus 1, okay, that for sure will give you 1 in here, right? So we'd like to replace this, the n minus 1, with something that equals to m times 2 to the power k. So this is 1 compensating 2 and 1. That means a to the power n minus 1 in here, m times 2 to the power k mod n will give you 1. Okay. So the trick is how to find the m and the k that could give you this. All right? All right. So basically, that's what you do in here. Look in here. Okay, so a to the power n minus 1. You replace it with this because you said n minus 1 as it was that. So this is if you format it better way. So it will be a to the power n to the power 2k. Then that means if k is 1, then you have 1, 2. If k is equal 2, then 2, 2, right? So it will be like a to the n 2, 2, 2, 2, k times. K times. Alright? So the Miller-Rabin test means from step 0 to step k minus 1. It's like you're looping it through the process. Okay. So the steps, I'm not sure this is the, okay. So the steps basically is you're gonna choose A and calculate t equals to the power m, which m equals, so basically the first step is to choose, okay, you have to choose t equals to a to the power m, okay, in which m equals n minus 1 divided by 2 to the power k, right? Because we said if you multiply the n with 2 to k will give you n minus 1, that's what we said, right? Alright, so you need to find t. So if t is plus 1 or minus 1, declare that n is a strong pseudo-prime. If t is anything else, then we cannot tell. Anyways, so it's basically, let's take example. Take a look at the example here. Okay, and we have to, I think we have to take a look at the algorithm a little bit closer. Okay, so basically in here, so using the base 2, okay, base 2, let, okay, does the number 561 pass the Miller-Rabin test? So using base 2, let 5, 6, 1, minus 1, this is n minus 1. What is n in here? 561. So 561 n minus 1 equals to 35 times 2 to 4. So what is the value of k? 4. What is the value of m? 35. So I was able to get m times 2 to the power k. K is 4, right? So m is 35, k is 4, and a is 2, right? Alright, so how many k's are you gonna have? 1, 2, 3, 4, right? So for k, for initialization, t equals what? There equals a to the power of m, which is 35. Mod 61 gives me this number. Alright? Then you know how it is. You keep powering to the 2, right? That's equal, it's like, right? Because we like k is 4, so you take the previous number and you power it 2. The previous number you power it to 2, right? So you take the previous number, you power it to 2. Okay, mod 56 will give you 166. Then you take the 16, you power it to 2, will give you 67. Power to 2 will give you plus 1. So if you come to the plus 1, okay, before you go through your k, the k, then it's a composite. Then it's a composite. Okay? So for 27, just check 27 if it's a composite or prime. All right. So is 27 a prime? Yeah. All right. So with the base 2, so n minus 1 equals 13 times 2 to the power 1. So what is the value of m? 13. What's the value of k? 1. Okay, and what is the value of a? Is a. So in this case, because k minus 1 equals 0, we should only the initialization step, t to the power 15 mod 17 11. That's it. There's no k. K is 0. Okay, and did not give you 1. So because of the algorithm never entered the loop that returns a composite. Returns composite. About 61 is a prime. Okay, so 61 is a prime. Again, we're going to use the same technique. So 61 minus 1, which is 15 times 2 to the power 2. 15 is the m. 2 is the k. So we have 2 loops, right? 2 loops. M is 15, k is 2, and 8. So here, the initial thing, t to the power 15, mod 61, 11. Remove the 11 to the power 2, mod k minus 1, then it's a prime. If it gives you minus 1, a prime. If it gives you plus 1, okay, then it's not a prime, okay? If it finishes before it gives you the plus 1, it's maybe. It's maybe, right? So that's, that's another algorithm for testing. Today, one of the most popular primality tests is a combination of the divisibility test and the Miller-Robin test. So in here, the number 4033, 4033, or 4033 is a composite. 37 times 107, so it's not a prime. Does it pass the recommendation primality test? So first of all, we perform the divisibility test first. Okay. So what we do with the divisibility test? We take the root, right? And we'll check the primary numbers less than the root. Okay, so 2, 3, 5, 7, 11, 17, 23 are not divisors for the 40333. They are not the divisors, right? The second one, we apply the Miller-Robin test with base 2. So again, 4033 minus 1 is 63 times 26. So what's the value of m? 20. What's the value of m?
36.
63.
63.
What is the value of k?
6.
1. Right?
6.
Yeah. It's supposed to be to the power 6, right? From here to the power 6. So what's the value of k? 6, right? 6. Right? 6, right? Which means m is 63 and k is 6. Okay. So when you do it after the first iteration, give you minus 1. That means what? It passed the test. So it passed the test twice, with the divisibility and with the Miller killer, right? With this algorithm, right?
But it wasn't time.
Yeah, that's the whole point. It passed in here, but did not pass in here, which is wrong. That's why it's probabilistic, right? So, but we are not satisfied. We continue what we do, what we said, what we have to do. We continue with a different pace. We try to do it with a different pace. Then it's what failed, right? It's failed. So we tried it with the pace of first rate, okay, and we try with different paces, it's failed. Anyways, so we'll come to the next topic, which is factorization. What is factorization? To factor a number. Okay, factorization is to, it's a very important topic. And it's a complex a topic that you know that you. So for example, if you have a number n, you need to factorize it. You need to factorize it. If you factorize it to elements, so it could be factorized to b1 to the power e1, b2 to the power e2, bk to the power ek, whatever. And there's two things you could calculate always when you factorize: the greatest common divisor and the least common multiplier. The greatest common divisor is very simple. Is so the first number and to the power of the minimum of the first number and the first two multiplied with the second common one to the power of the minimum of both, and so on and so forth. For the least common multiplier, it will be with the max, not the minimum. Alright? So what you need to know also, the least common multiplier multiplied by the greatest common divisor, it will give you the value of a multiplied by b. A multiplied by b. Okay. So again, there is different ways to do factorizing, different ways. So the first one is trial division method. Trial division method, right? So for example, 10. You would like to know how to factor. If you try with 2, does it work? Yes. 2 times 5, right? Triangle. But you know this will work for smaller numbers, but for big numbers it will be very difficult, right? Right? So if I give you, for example, if I give you a number like this, 7, 6, 8, 5, 6, 1, 1, 3, 2, 3, 1, or 3. Definitely does not divide by 2. Definitely does not divide by 5, but what else you can try? To see if you divide by 3, right? Maybe, maybe not. But what if it's like more numbers, right? Alright. So divisibility, it will work with smaller numbers, but not with bigger numbers. So use the trial division algorithm to find the factor for 12, 33. So yeah, this worked in here, 3 to the power 2 times 137. How about this number, bigger number? Okay, it was like 2 to the power 3 times 3 to the power 2 times 13 times 37 times 4,003,987. Okay, so definitely it's not the way to go. Alright. So the first one, the technique is trial division method. The second one, and this is a very complex English. The problem is the complexity. So the complexity is exponential. Anything the complexity exponential, that means hard to implement and hard to use. The second technique is Fermat method. Alright, and the Fermat factorization method, where we divide a number n into 2 positive integers, a and b, not necessarily a prime. So that n equals a times b, n equals times b, right? So n times it, so n equals a times b, and it equals x. We have to look for x squared minus y squared. Okay. So that means a equals x plus y, where a equals x plus y, and b equals x minus y. X minus y. So you're trying here to look. The method tries to find numbers a and b close to each other, almost the same. you know, a and b close to each other, it starts from the smallest integer greater than x, okay, where x is like root of n, and try to find another integer y such that the relationship is y squared from here, y squared equals x squared minus a, x squared minus minus n. So you keep iterating through that until you find like the numbers, the y and x that they fit that number. All right. So again, this is like by iteration, right? The other way is to have a polar p minus 1 method, polar minus b minus 1 method. All right. And to be honest with you, I mean, I did not look at the proof for this from math, so just they are listed in the book how they work. But I was interested myself to see how they proved and how they work, but I did not have time for that. I did not have time for that over 5 semesters. I've been teaching this time many times, so anyways. So just I need you for this course just to understand the main concept here. The main concept that we need to know primes, we need to know the theories, different theories that we have learned, and we have to understand the need for factorization. And the most important thing, why is it listed in this book not to do it, on here, just to show you the complexity for factorizing. So why we pick, I mean, you need to make a logic, right? So why we pick like big primes? Because we need to be, the tendency to be able to factorize them. And then here we try to show you the complexity of the process. Alright, the complexity of the process, okay? So Pollard P minus 1, so basically in 1997 John Pollard developed a method that finds a prime factor P of a number based on the condition that P minus 1 has no factor larger than predefined value b, which is the boundary or the bound. Alright? So basically it says, okay, the p, the greatest common divisor for 2 to the power b factorial minus 1 and n. Alright? And in here we have the algorithm for you in here. And again, this is a complex. The complexity is O 2 to the power n. It's not exponential, but it's still a complex. Actually, there is an example in here. Use the polar p minus 1 method to find factor for this with the boundary b. So we run the program. There is a code in here. You could, run the program. And so it gave you with this result. It gave you this. So it's like an algorithm. There is another algorithm after the polar method called Pollard row. You know the letter row in Greek, row method. All right. The same thing. I mean the same thing. So the process is. You assume, so that's a row, row, successive members, alright? So you assume that there is 2 integers, x1 and x2, right? You assume there is an integer x1 and x2 such that p divides x1 minus x2, but n does not, right? Start with this assumption, right? I mean, I wish that you have your book with me, that will help you to follow. Anyways, there is another technique. So could take a look at this, there's another called the quadric sieve, and did not explain it in the book, just gave you the complexity of it, okay? And there is another one called number field sieve, did not explain how it works, but give you the complexity, right? The complexity of that. So all I need you for the sake of this purpose is to understand factorization is a complex process. There is different algorithms or different techniques to factorize any number. Okay, factorize a number. Okay, and no matter what you use, it's a complex. It's a complex. Okay. Good. So we're gonna come to a very important concept, which is Chinese. So for the factorization, just you don't have to delve deep, but for the Chinese remainder theorem, that's something that you have to understand very well. Okay? And it's very important. So the Chinese remainder theorem, it says, which is CRT, short as CRT, is used to solve a set of congruent equations with one variable but different moduli, which are relatively prime as shown below. So we have three equations as you see here. The first equation, x. So there's only one variable. What is a variable? X. You're gonna look for x. So x modulo m1, okay, will give you a1. X modulo m2 will give you a2. X modulo ak, for example, will give you modulo mk will give you ak. So what's the condition? M1, M2, M until mk, what they are? They're relatively prime. Okay, that's a condition, right? So set of equations, find x code. Alright. So the steps, there's the steps that you have to follow, and they are listed in the book for you, 4 steps. Exactly 4 steps. So for example, in here, the following is an example of a set of equations. So we have x modulo 3 will give you 2. X modulo 5 will give you 3. X modulo 7 will give you 2, right? So the first condition, let's check the first condition. Are 5, 7, 3 relatively prime? Yes, they are relatively prime. Alright? They are relatively prime. So the solution for this equation, so first of all, okay, the result is x is 23. Try 23. So for example, 23 modulo 3, how much? 23 modulo 3, how much? 2. 23 modulo 5? 3. 23 modulo 7? 2, right? So the answer is 23, alright? So how we can go, how can we get this one? So there's steps. The first step, number 1, 4 steps, okay? And you should expect a question in the exam, you know. So the first thing you have to find the M, capital M. What is a capital M? Is the multiplication of the M's in the modules in the equations. If you have 3 equations, so how many number are you going to multiply? 3. M1 times M2 times M3, right? In our example, what are the M's? 3 times 5, what is a big M? Equal 3 times 5 times 7. So you calculated what? The M. Okay? Then after that, you'll find capital M for each equation. So M1 equals our M divided by M1. M2 equals to M divided by M2, and so on and so forth. Then after that, we find the multiplicative inverse for M1. So we'll find M, capital M. Then we'll find capital M1 for equation 1, capital M2 for equation 2, M3 for equation 3. Then after that, we'll find the inverse of this M's, the inverse of this M's. So M1 to the power minus 1, the inverse is right. Okay. Then after that, we use this equation to find the value of x. So it's a1 times m1 times m1 inverse plus a2 times n2 times n2 inverse plus m3, m4 until n. Very simple. So let's see how it works. Okay. So the first step again, what we'll find? That capital M, which is 3 times 5 times 7, which is 105. Number 2, we'll find the capital M's. M1, 105 divided by 3, which is 35. M2 is 105 divided by 5. M3 is 105 divided by 7, which is 15. Now, I have to find the inverses. I have to find the inverses. Modulo what? Inverse, I mean, when you talk about inverse, is modulo, right? Modulo something. So for M1, it will be modulo what? 3, right? For M2, it will be modulo 5. For M3, it will be modulo 7. So you find the inverses. Anyhow, the inverse of M1 is 2, the inverse of M2 is 1, the inverse of M3 is 1. Then we multiply them together. 2 times 2, what is 2?
Okay,
2 in here, what is 2?
A1,
Okay, M1 times
M1,
M1 times
and -1.
the inverse. And you do it and add it, so, and modulo 105 give you what? 104. That's the result. So if I give you a set of equations, it has 5 equations, 10 equations, okay, 20 equations. Okay, what is the first thing you have to check? And until you find x, what is the first thing you have to check?
M,
Before that, you have to check that the modules are relatively prime. They are relatively prime. Okay, then after that you have 4 steps. So step 0, step 4, there's 4 steps. Step 0 is to make sure they're relatively prime. Simple? Alright, so in here, find the integer that has the remainder of 3. Okay, so that's another question. Remainder of a 3 when divided by 7 and 13. So the remainder is a 3 when divided by 7 and 13, and divisible by 12. That means the remainder how much? 0. So you build the 3 equations, and you have to solve them. So you follow the steps, you'll find that, you know, anyways, you follow the steps, okay, and you solve the problem. So it says in here, assume that we need to calculate z, which is x plus y, where, give me something, make sure. So the application, the Chinese remainder theorem has several applications in cryptography. One is to solve the quadratic congruence as discussed in the next section. The other is to represent very large integers in terms of list of small integers. So for example, you have example in here, assume that we need to calculate z, which is x plus 1, where x is 123 and y is 334. So that's the value of x, and that's of value of y. We need to calculate z, but other system, our system accepts only numbers less than 100. So these numbers can be represented as follows. So I mean, you cannot. It has to be less than 100. I mean, less than, and these numbers are bigger than 100. So how? So you're looking for x. You can represent a value for x. Okay, modulo 99. So what would be the value? Okay, not modulo 99, modulo 99, so 24. So 123 modulo 99 gives you 24, right? Yeah, that's what it is, x, so x is in here. So, x 123 modulo 24 will give you 99, x modulo 98 will give you 25, and x modulo 97 will give you 26. It's the same thing we do it for the y. So x plus y, so you add them. 24 plus 36, 61. 25 plus 40 will give you 65. 26 plus 30 will give you, okay. So x plus y modulo 61, okay. So basically this will allow you to represent the data and represent the data in less than 100. Now 3 equations can be solved using the Chinese remainder theorem to find z. One of the acceptable answers is z for 5, 7, which is the answer for adding, adding. So basically what it says that the system cannot accept representation over 100. So instead of representing it with one number, one equation, we represent the 3 equations. And when we calculate that, then, now we come to quadratic congruence, which is much more complex. Solve equations in the quadratic. Okay. So before what we did, linear, right? Congruence, right? Anything above power of 1 will become quadratic, right? So in cryptography, we also need to discuss quadratic congruence, that is equations of the form of a2x to the power multiplied by x to the power 2 plus a1 a0 equals 0 mod n. Alright? So what we are trying to say in here, okay, what we're saying, I mean the simplest thing is to have integer, right? 5 mod 3, right? That's the simplest thing. You have integer mod something. Let's make it a little bit more complex. You could have like number to power something mod something, right? Little bit more complex. Make it much more bigger complex. 9, 8, 7, 3, 1, 2 to the power 4, 3, 2, 5 mod something more complex, right? Right? Easy to solve. It's numbers, right? Now you could have equations. You could have x, okay, mod, for example, something, right? It could be x plus 1 mod something, right? It could be quadratic, n x squared plus 1 mod, right? Right? Okay, so you're trying to build the system, right? Okay, so this is very easy. It's numbers for you to solve. This is like equations. Okay, so it could be much more complex, right? Okay, so in here, for example, if I would like to solve this equations, x squared modulo n equals a. So I need to find the value of x. Okay, it could be like this. It could be like, for example, x squared, okay, 3 mod 99. Give me the value of x. Supposedly, how many value it's supposed to have for x here?
Can we just like consider x squared
What?
equal? Let's consider x squared equal like value of y, and then use the same.
Anyway, there's an equation that you have to solve in here, right? So usually when you have like a quadratic equation, how many solutions do you have? Two, right? Okay,
Yes,
so
of
how we
course.
solve these problems, right? Okay. Yep. I mean, alright. So that's the whole idea. It could be much more complex. It could be like, go figure, right? Okay. So basically, we're trying to say that we are used to have equations like that, plus 3 equals 0. That's what we learned in high school. Okay. Now we are dealing with module equations, module. Alright? So I'm sure that it's not as simple as, you know, alright, so quadratic congruence modulo prime and quadriconvergent modulo composite. Alright. So we first consider the case in which the modulus is a prime. Okay, anything with a prime supposed to be easier, right? Okay, so take a look in here. So the first example, the equation x to the power of 2 modulo 3 equals 11. So how many solutions we're supposed to have in here? 2 solutions, right? What are the solutions? X equals 5, and the other one, x equals minus 5. Okay, let's try it. So 5 power 2 equals 25. Modulo 11 would be 3, right? Right? Right, guys? So x squared so the solution they told us is 5 and minus 5. So let's try it. 5 squared. Is that correct? 25 modulo 11 gives you 3, right? Okay. How about minus square? Same thing, right? Same thing, right? So this is solution, right? So the solution are actually the minus 5. We don't like, remember that we don't like to use the minus. So the minus 5 equals to what? To 6, right? So minus 5 plus the modulo equals 6. So what are the set of solutions? 5 and 6, right? Let's try it with 6. Let's remove this 6. 6 squared, how much? 33, 36, right? All right. Modulo 11, how much? All right. Okay. So the equation x squared modulo 11 2 has no solution. No integer x can be found such that x squared modulo 11 gives you 2. So there is no solution. There is no solution. There is something called the quadratic residue and non-residue. So the residue and non-residue. So in the equation x squared a x squared a here, it's here, x squared a mod b, a is called quadratic residue or QR if the equation has 2 solutions. So if the equation has 2 solutions, what we call it? QR. A is called the quadratic non-residual Q and R if the equation has no solution. So some of the equations have solutions, we call them QR, and some of the equations have no solutions, we call them Q and R, right? Alright, so it can be proved that N, Z, okay, yes, okay, so it's like a set, it's a multiplicative set for primes, okay? So what are the members again? 1, 2, p minus 1. Okay. What is the value of 5? It will be p minus 1, right? So how many elements are relatively prime? P minus 1, right? P minus 1. All right. So p minus 1 elements exactly with p minus 1 elements exactly p minus 1 over 2 elements are quadratic residue. Okay, so we have p minus 1 over 2 QR and p minus 1 over 2 r what? Q Let's take example. So if you take this example, there are 10 elements in the Z11. Okay, the Z11 here, the Z11 multiplicative. There is 10 elements. Exactly 5 of them are a quadratic residue and 5 of them are non-residual. In other words, Z11 multiplicative is divided into halves. One half QR, the other one is Q and R, as you see here. So Z11, the members are 1, 2, 3, 4, 5, 6, 7, 8, 9, and each element has a square root in here. Then they are part of the QR, and in here each element does not have a square root. They are part of Q and R. So in simple words, I see maybe you're lost. Okay, in case you're lost, let's just refresh. So in here we're trying to solve a quadratic equation, but this is not like regular equations that we used in high school, equals 0. Here is a modular equations. So it could have a solution and could not have a solution. If it has a solution, how many solutions can it have? 2. If it does not, will be 0. The ones have a solution, we call them Q, R. The ones don't have solution, we call them Q and R. Alright? Alright? So it will be difficult to figure it out if it's any number. But if we use the prime numbers, as you see in here, if you're using the prime number as you see in here, it will be half and a half. Half and a half of the set. Alright? So Euler's criterion. Euler's criterion. Okay. So what's Euler's criterion? It says, how can we check to see if the integer is QR modulo B? Euler's criterion gives a very specific condition. What are the conditions? It says if A to the power p minus 1 over 2 equals 1 mod b, A is a quadratic residue. If it equals minus 1, then A is a quadratic non-residue. So here is an example. So for example, to find out 14 or 16 is QR in Z26. So what is the set? Is multiplicative Z23, I'm sorry. Z23. Alright, so we'd like to know if 14 is a QR or a QNR. Very simple. So 14 to the power 23 minus 1 over 2, okay, will give you 22, and will give you minus 1, then it's not residual. How about the 16? It gave you 1, then it's residual. Then after that, we talk about solving quadratic equation modulo prime, right? And so you don't have to worry about it. Take a look at it. I don't think I have time to explain it. Then we'll go to the last section. Which is exponentiation and logarithm. Alright. So what we are trying to say here, what we're trying to do is a lot of the key calculation for you know what's exponentiation, right? Like e to the power something, right? So like, y equals a to the power x, for example, e to the power x, right? So you could, what is the reverse process for exponentiation? Logarithms, right? The logarithms. So many of the techniques that we're gonna use in algorithm is creating the key through exponentiation. Alright? So how to do it? That's number one. And remember, this is exponentiation usually also is like modulo something, right? Modulo, not normal. And we need to prove whatever we do, it has to be complex, because the cryptanalysis, what they try to do, the logarithm. Try to get the, so how to reverse the process, okay? Logarithmic, okay? So how they can, get the logarithm, right? Anyways, so in here, just I'm gonna give you a few hints. I mean, just to know what's happening. I mean, so it's exponentiation and logarithms, right? So basically, so from here. So usually what you try to do, find y, try to find y, a, x, right? Okay, all right. So you're trying to find, for example, your key. Let's say this is the key, having integer, and you get the exponent x. The reverse process is what? The reverse process is trying to find the x. Finding the x, okay? Finding the x, which is log a for the y, all right? So let's say that your key. Let's say this is the key, right? You generate the y of it, all right? Let's say the cryptanalysis found the y. What he will try to do to find your key, the x, right? So definitely what you're gonna do in here to try to make the key is complex, right? Big, large. That the reverse process will be very complex, all right? So they're gonna use discrete logarithms to try to find your x, okay? That's the whole thing, okay? So the idea behind the square and multiple, okay, so what are you trying to do here? And again, all right, we are not so simple anymore. We've grown. We're not babyish anymore. Okay, we don't use it like symbol like this. Okay, do we use a symbol like this? No. Whatever we do in here, we're gonna go mod n. Right? That's a modulo n. All the processes we have in here, modulo n. If I do the reverse, for example, log, okay, x equals log a using y, okay, ln, okay, logarithmic n, okay. So for example, this is where is it used? In the RSA. We're going to talk about it next week. That's how we generate the keys, right? In the RSA. So we use a very large exponents. Unfortunately, most of the computer languages have no operator that can efficiently compute exponentiation, particularly when the exponent is very large. To make this type of calculation more efficient, we need algorithms that are are more efficient, right? So we need to be able to calculate So in here they talk about free algorithms. Okay, I'll leave it for you to read it, to enjoy it one more time, and then the last thing is the logarithms. So in the logarithmic, we also need to discuss modular. So in here, we have to explain a lot about the modular arithmetic. We could go over it, but it's the reverse process. Anyways, just I need you for this course just to have an idea, so let me go backwards. So what backwards in what we have covered today? We ended with exponentiation and logarithm. Why we need to know exponentiation? Because we're gonna use these to create the keys and the system, right? All right. So we have to have a large number to exponentiate to a very, very large number. The x in here could be like 500 digits. All right. So if you try to do it in your calculator, it's not going to work. All right. It has to be like iteration. So there is different algorithms for that. You have to understand the reverse of this process is discrete logarithmic. Okay, where you're trying to find the x from the discovered y. Okay, so again, there is a lot of algorithms to do that. Okay, it's like a fight between the two things. Okay, so what we need to understand that the complexity is huge in both, and there is algorithm to do that. That's all I need you to know here. Just take a look at the different algorithms. Then after that, before that, we covered. So that was section 9.6. In section 9.5, we spoke about quadratic congruence. What's a quadratic congruence? All right. So we said that you need to solve problems modulo. Okay. So for example, x squared equals a mod n, for example. So what is the value? So we need to be able to, for some of the algorithms, to find this x, by the way, it could be your key. Okay, your key, right? That you're trying to use. So there is different algorithms. Remember, in this class, we're just teaching you math. We're not teaching you certain encryption technique or something yet. I mean, we teach you the math. Then in the previous section, we learned about a very important theorem, which is CRT. Anybody remember the CRT? Chinese remainder theorem. Well, you'll be able to solve multiple equations. So you could have ax, okay, a1 mod m1 x, a2 mod m2 x, a3 mod m3 the same. So how many steps to solve these equations? 5 actually. Okay, starts 5. Starts from step 0 that we have to find these r relatively prime. Number 2, we have to calculate the capital M. Then we have to calculate M for each one, M1, M2, M3. Then we have to calculate the inverses. Alright? Then we use the equation to calculate what the value of x. Very simple. That's it. Okay? So this is a very important that you have to know at A to Z, the Chinese remainder theorem. Alright? Then before that, what we were talking about? Factorization. So factorization is a very important to know, and who used the factorization? Who needs to know who used the factorization? Usually the cryptanalysis, right? So usually, like you start with the prime yourself. You start with the prime, okay, and so n equals p times q, okay, and these are primes, okay. N maybe becomes public information. They don't know how it was built from 2 prime, right? You'll see it next week, right? So n, the cryptanalyst could find it. Their next job to find the key is to divide it into parts. What we call this? Factorization, okay? To get the factors, right? So this is a very complex problem, and we spoke about different, different ways for factorizing it, like trial and division, Fermat method, the raw, different things, right? Then before that we're going backward, we spoke about primality test. If the number is primary or not primary. Okay, 2 things. Checking if it's prime, not prime, and generating primes. So these are both talents that you or whoever write the code needs to have. You have to be able to check this huge number, this is a huge key. Is a prime or not a prime? Why? Because that's your algorithms, what they require, how they kick off, how they start looking for primes. So next week we'll see in RSA, you start with 2 primes, pick 2 primes. And these 2 primes has to be huge. Multiply them together, even becomes n, much bigger, right? Alright, so prime, but it has to be primes. It has to be primes. Okay? Let's say that we have the condition, the minimum size of the prime is like 5. Oh, usually one of them huge, the other one smaller, for example. Okay, so one of them like 500 characters, numbers. Okay, so you have to understand also how to deal with primality, right? And then how to generate a prime. We give you a few techniques to how to generate a prime. Okay, so if I tell you right now, I need a prime number which is built of 66 numbers. You're not going to try randomly the first number. So any number you try, what will happen? You have to test if it's a prime.
Yeah.
All right.
Fine.
All right. So okay. So you have to find one of the generators. Okay, and then still you have to test it. So at least when you use these generators, you are like 99.9% this is prime. Just you have to test it. But if you just randomly trying number, I mean, you know, you might generate like 100 numbers before you come to a prime. So you have to test 100 times, right? So that's the other thing. Okay, I'm trying to put everything together. It's very important to put everything. Why we learning that? How important it is. This is, you know, so we have to put everything together, right? And then before that, we start talking about the primes. Define that the numbers could be number 1 prime, could be composite. And you know how we can find the number of primes in before the number, and how can we detect you know the prime. Then we spoke about the Euler phi function. All right, but and different things. So I think now we have learned enough math for next week. All right, enough math for next week. And so I'm sure that when you go through it, you'll enjoy it. All right. And if you have questions, you always can ask. Any questions now? Yes.
Do we have to remember all this for the letter?
Well, for the midterm, you could
Is it
close.
optional?
You could. Hello. Thank you. Bye. Bye.